This video will cover a number of key spectral features in NMR spectra to help analyze the spectrum so you can identify which molecule or which types of atoms are present in that molecule. So the first we'll talk about is the number of signals or the number of peaks. This indicates the number of hydrogens in distinct chemical environments or groups of hydrogens in distinct chemical environments. Then we have the chemical shift of signals. So this is where that peak is on the spectrum, and that gives information about what we'll say the electron shielding environment or functional group or atoms around a distinct group of hydrogens. Then we have the integration of signals, which indicates the relative number of hydrogens in each distinct environment for a molecule. And then the splitting of signals, which gives information about neighboring hydrogens. So we'll talk about each of these in more detail. So first is number of signals. And the significance here, notice it says the number of hydrogens in distinct chemical environments. So we have one example here, methane. Methane has 4 hydrogens. They're all bonded to the same exact carbon. So as far as chemical environments go, they are in the same chemical environment. And so methane produces one signal, 4 equivalent hydrogens, but they would all show up as the same signal. So just one peak. Then we have ethane. Now, ethane has 6 hydrogens. Each of them are bonded to a carbon that's bonded to another carbon with another CH3 group. So there is a plane of symmetry down the molecule, and so all 6 of these hydrogens are in the same chemical environment. They are equivalent as far as NMR goes, and so they also would produce one signal. Now here's a molecule that would produce 2 signals. We do have a plane of symmetry down the center, but we have 2 CH3 groups on the ends and then a CH2 in the center. So the CH2 cannot be the same as a CH3 group. That will produce its own signal. So those 3 orange hydrogens are producing a different signal than the CH2. And then this CH3 is the same signal as the other CH3 group because of that plane of symmetry. Because you can exactly reflect the CH3 groups across that plane, and they're in the same environment. They're all bonded to a carbon that's bonded to a CH2 that's bonded to a CH3. So here we have 2 groups of hydrogens, so that would produce 2 signals. One signal corresponds to the 2 hydrogens in the center, the CH2 group, and the other signal would correspond to the 6 hydrogens in the CH3 groups. Okay, so as you're looking at a molecule, you're identifying hydrogens bonded to different carbons. They would each produce a different peak unless you have a plane of symmetry in the molecule. And in that case, they would be the same peak. Okay, so now we have chemical shift. This is the location of peaks on a spectrum. This gives information about the functional group. So this is probably the most similar part to IR, where you can identify location of peaks on an IR spectrum, and that gives information about a functional group. Pretty similar for NMR. So notice the x-axis is ppm, or that lowercase delta. We'll describe that as chemical shift. And then a bunch of different functional groups throughout. And notice this is all for proton NMR. We'll talk a little bit about carbon NMR as well, but mostly proton NMR. So a couple that I'll point out, saturated alkanes, so no double bonds, are low ppm, or we say this is upfield. Alcohols have a pretty wide range, but between about 1 and 5.5 ppm. Carboxylic acids are all the way over here. So they have really high ppm. They're downfield. Notice aldehydes are right here, aromatics, So as needed, you can use this to identify what functional group might be present in the molecule based on the NMR spectrum. Okay, then we have integration of signals. So this tells us information about how many hydrogens are in each distinct environment. So for methane, we said methane would produce one signal. That signal corresponds or represents 4 hydrogens. So the integration of that peak, and this is like when you take an NMR using the actual NMR instrument, you can have it provide integration information. This would probably indicate integration of 1. Although it's 4 hydrogens, it gets reduced to the lowest value. So let's look at propane. This is a better example. We said that there are 2 groups of hydrogens that produce 2 signals. One signal corresponds to the 2 CH2 hydrogens, and then the other corresponds to the 6 CH3 hydrogens. So we have 2 signals. The integration ratio between those 2 signals would be 2:6, but we can divide both of those by 2, so it would be indicated on the spectrum as 1:3. Just reducing to the smallest whole number value. Here's another example, propanoic acid. So propanoic acid has 3 groups of hydrogens. We have, this first CH3 group on the end, that would produce its own peak. Next, we have the CH2. That CH2 would produce its own peak as well. And then we have the OH. So the first signal would correspond to the 3 CH3 hydrogens. Another signal, sorry, this highlighting is a little bit out of order. Another signal would correspond to the 2 light pink hydrogens, the CH2 group, and then the last would be that 1 hydrogen from the carboxylic acid group. So this molecule would produce 3 signals, and the integration ratio is 3:2:1 or 1:2:3. We can't reduce those numbers to a smaller whole number, so they would be exactly as they are in the molecule. Okay, so we've got number of peaks to tell us hydrogens in distinct chemical environments. We have location on the spectrum, can give information about functional group, and integration of peaks gives information about number of hydrogens represented by each peak. Now there's one more feature, which is the splitting of signals, and this provides information about neighboring hydrogens. So this is very helpful when identifying the structure or possible structure of a molecule, because not only are you analyzing and getting information about a group of hydrogens, the splitting of the signal for that group gives information about the neighboring hydrogens. So it gives some indication of what the bonding looks like in the molecule. So here's an example. We already know what the structure of the molecule is, but we could predict the splitting. So signals for a group of hydrogens are split by neighboring hydrogens by a factor of n+1, where n is the number of neighboring hydrogens. Now, this is a general rule. There are certainly exceptions to the n+1 rule. We're going to go just based on it for now. We can look at exceptions in the future. So let's look at the green hydrogens on the left, that CH3 group. So when you're looking for neighboring hydrogens, you're looking at the carbon bonded to the carbon that the CH3 group is. So this is where that CH3 group is bonded, right? They're bonded to that carbon. So we'd look at any other carbons bonded to it. And that's this one. There are 2 hydrogens bonded to that neighboring carbon. So the signal for the green carbons is split by the 2 hydrogens that are neighboring. So split by pink hydrogens. There are 2 there. So the peak for the green hydrogens would show up as a triplet because we have 2 pink hydrogens, and then so that's n, and then +1 is 3. So the way a triplet peak looks on a spectrum, instead of just 1 signal for a peak, it would be split into 3 very close together. So that's generally what a triplet looks like. Usually the center peak is higher than the other, but that is not something we'll analyze in our class. Okay, so that's for the for the green hydrogens. For the light pink hydrogens, the CH2 group, they are bonded to that carbon. So it has two neighboring carbons, this one and this one. So these two are the two neighboring carbons for the CH2 group, the pink CH2. So now we're looking at total number of hydrogens bonded to the neighboring carbons. The neighboring carbon on the left has 3 hydrogens bonded to it, so those will split the signal for the CH2 group. The carbon on the right is not bonded to any hydrogens, so that carbon does not contribute to the splitting of the CH2 group. So the CH2, the light pink hydrogens, are split only by the green hydrogens. There are 3 of them. So that ends up, if we do 3 plus 1, that's 4. So this peak will look like a quartet, which is 4 small peaks instead of 1 large peak. All right, so that's the CH2 group. Now, if we look at the OH group, that's bonded to this oxygen. The oxygen has 1 neighboring atom, which is this carbon. That carbon does not have any hydrogens bonded to it. It's not bonded to any. So there are 0 neighboring hydrogens. So this OH group has no splitting. 0 plus 1 equals 1. So this will just look like a single peak. So I think I have the NMR spectrum on this slide. I don't. We will look at the NMR spectrum for this molecule so you can see what the splitting looks like. But here's the table to predict what the peak splitting is based on number of neighboring hydrogens. So we've seen singlet so far. We saw triplet and quartet. If there's 1 neighboring hydrogen, that would produce a doublet. 4 neighboring hydrogens produces a quintet or multiplet. So once you get higher than 4 or 5 hydrogens, it's hard to visually distinguish between 5 peaks, the quintet, or 6 or 7. So often those are described as a multiplet. So that tells you there's 4, 5, or more neighboring hydrogens. There's a limit to the resolution of NMR spectra based on the instrument that you're using. So with that limitation, it's hard to see those individual peak splittings. Okay, so here's the NMR spectrum. We just talked about propanoic acid. We know that the CH3 group has its own peak. The CH2 group has its own peak. The OH group has its own peak. CH3 group should be a triplet. CH2 group should be a quartet. And the OH group should be a singlet. Also, if you recall, carboxylic acid hydrogens, so that's the bright pink 1H, has a very high ppm. And you notice we have this signal here with a very high ppm, and it is a singlet. That is the OH hydrogen. And then this is what I'm saying. If you look at the other 2 peaks, sometimes it's hard to identify triplet versus quartet. But if you look closely, this one is a triplet. So that aligns with the CH3 group. And then this one is a quartet, and that aligns with the CH2. So I think I have all these highlighted. I don't. But there we go. So we have this one is that peak. The quartet is this one. And the triplet is that first one. Let's look at another example. Here's propanaldehyde. So we have a CH3 group that's split by these 2 neighboring hydrogens, so that's a triplet. The CH2 group is split by this CH3, that's a quartet. And then that hydrogen, the aldehyde hydrogen, is not split by anything, so that should be a singlet. So this has a very similar NMR spectrum to propanoic acid. And then looking at the spectrum, let's see, we've got the singlet with a very high ppm that aligns with an aldehyde hydrogen. We have a hard to visually see, but that is a quartet peak, and that aligns with the CH2 group, and then the triplet aligns with the CH3. Okay, so those are a couple examples of proton NMR. Again, we've got number of peaks to give us number of unique groups of hydrogens. Peak splitting gives information about neighboring hydrogens. Location on the spectrum gives information about functional group. And then integration of signals isn't provided on here, but sometimes if you're just given the spectrum, you might have information like integration is 1. Integration is 2. Integration is 3. And that would give you more information about the groups of hydrogens. Okay, so I said we'd talk a little bit about carbon NMR. This works very similarly to proton NMR, but tells you information about the carbon atoms instead of the protons, the hydrogens. This is less sensitive than proton NMR, but still helpful. Carbon NMR signals are split by adjacent carbon atoms. They have different locations on the spectrum, on the x-axis, due to different functional groups. Again, we have alkanes, pretty low ppm. Carbonyls are all high ppm, and then we've got, everything in between. So you can use this as a reference if you're trying to identify groups of carbon signals. Now, it's often hard to really tell the difference, especially at the level that we're learning in our class, between peaks on a carbon NMR spectrum. We can expect number of peaks for sure. This works the same as proton NMR, but notice that we don't really have a lot of resolution for peak splitting. It's difficult to do that for carbon NMR. So we have a little bit less information, or distinct information with that spectrum. But looking at this molecule, so here's ethyl propyl ether, we would expect 5 different peaks. There is no symmetry in this molecule. So the CH3 has its own peak, then that CH2 is different than this CH2, which is different than this one, which is different than this one. So 5 different peaks for 5 different carbons. They would be split by neighboring carbons, but again, we don't have that resolution in the NMR spectrum. What we could tell is that the yellow and green, so these 2 carbons, would be more downfield, so higher ppm, and that's because they're closer to an oxygen. Generally, as atoms are closer to more electronegative atoms, like closer to the oxygen, they would show up with a higher ppm or more downfield. So the yellow and green peaks would be about these 2. And then to tell the difference between the CH3 that's blue, the pink, and the orange, that would be difficult for us at our level. So you won't be doing that, for our class without any additional information. Now I just have this last slide. This is back to proton NMR. And the goal here is really just to show you how symmetry plays a role in proton NMR. The spectra that we've looked at so far, those molecules did not have a plane of symmetry. But here's one that does. So this is para-bromoethylbenzene. We have this benzene ring. We have bromine para to the ethyl group. So the plane of symmetry here is kind of through those para groups. So notice that this hydrogen is labeled as HA, and so is this one. These are in the exact same chemical environments. They're bonded to a carbon that's bonded to a carbon that's bonded to a bromine. And then if you look in the other direction around the ring, we've got the exact same bonding pattern. So they're in the same chemical environment. They show up as the same peak. Here is the HA peak. That's in the area of aromatic carbon to hydrogen bonds. If you look at the table with different chemical shifts for different functional groups. And then HB is very close. So let me erase these. HB right here, very close to HA, slightly more upfield or lower chemical shift because it's further away from the bromine. And then C and D would have their own peaks further to the right, so lower chemical shift or upfield. We have a triplet for HD because it is bonded to the CH2 group. And then we have a quartet for HC because of the CH3 group, and then the other neighboring carbon doesn't have any hydrogens there. Now this peak is a reference peak for 0, so usually something is added that has a chemical shift of 0, and that provides reference information, so you know that all other chemical shifts are higher than 0 for a molecule. So I'll label this as a reference peak. Okay, so that's all I have for this video. We will do more examples in class.